Hello, everyone. I have a cat standing on my back. Today's video is going to be me going through correlations today. So one of the types of research methods you need to know, something students do tend to struggle with quite a bit. Bella, I've no idea what you're doing. Can you get your ass from the back of my head, please? So we are going to be going through correlations today. If I can sort out my life. We're going to be going through correlational hypotheses. We're going to be going through how to actually write a... Oh my God, you're using all your claws. So if I move to this slide just here and we make a proper start, what is a correlation? Right? What is a correlation? What are correlations? Right? Correlations are basically a way in which you do research, like experiments or observations. But they're not unlike experiments. They're not trying to find a cause and effect. They're not trying to find one thing have an effect on the other. They're less scientific than that. So correlations are basically an attempt to try find a relationship between two covariables. A crucial thing to write down, by the way, is that correlations do not have IVs and they do not have DVs because they're not trying to find an IV affect the DV. Correlations are merely just trying to find a relationship. Pardon me, I'll try to edit that out. A relationship between two variables. And what we mean by that is that they're not trying to find one thing affect the other. There just seems to be, when you've got two different covariables, when that one goes up, well, that one kind of tends to go up. You're not saying that this variable affects that variable, makes that variable move. It's just saying that there may be something between them. So you can kind of see how it is less scientific, because an IV is literally saying, an experiment literally says that IV is affecting that DV. It's having a direct impact on, it's manipulating, it's influencing, it's impacting that DV. Whereas correlations are a bit like, well, there may be something between them. So there are, by the way, thousands of really weird correlations. So, for example, the one that always stayed in my mind when I was at uni, if you put these two graphs together, they go up at and then go down and then go up at almost exactly the right moments. And the two covariables I'm talking about here is the popularity of Justin Bieber, starting to rise in, I think, 2008, 2009, I think it was, is almost perfectly correlated with the number of incidences caused by Somali pirates. Those two things, if you plot them on a graph, are really correlated. Now, you can't, Justin Bieber's done many crimes before, but you can't say that Justin Bieber's popularity is causing Somali pirates to, attack from the coast, the African coast, for example, off Cape Horn. I think it's called Cape Horn. So a correlation is there is simply two variables. Now, one thing you do need to know are correlations are shown via scatter graphs like the ones down the bottom. Now, you do need to know what we mean by a positive and a negative correlation, and that will come with time. Very simply put, by the way, a positive correlation, which tends to, well, rather a strong positive correlation, which tends to go this way, is when one variable goes up, the other one goes up, or if one variable goes down, the other variable goes down. So, for example, if sea level goes down, there is a relationship that there is a correlation that then the number of fish in the sea go down. You can't definitively say that one causes the other, and in correlations, we're not saying one thing causes the other, but that would be a positive correlation when both variables move in the same direction, though one is not causing the other one to move in that direction. A negative correlation, which tends to go this way, is what we call an inverse relationship, where when one variable goes up, the other variable will go in the opposite direction. Again, one of these variables is not causing the other. There just seems to be a relationship. So off the top of my head, and you could say, yeah, but this does cause it. But I'm not saying that. I'm not saying that. As the degrees, as the number of degrees centigrade goes up, so the heat of the day, the fewer clothes people wear. Now you may say, well, the sun causes me to take my clothes off. Yeah, but a correlation doesn't say that. A correlation is only trying to find a relationship. The last thing to note, and this is quite important about correlations, because it may kind of help what I just said. Correlations are often done prior to an experiment. If you do find a strong correlation, there is a good chance that one of those variables did impact the other. There's a good chance, not with the Justin Bieber one, but there is a good chance that one variable did actually affect the other. So, for example, if I found that the number of sun hours in the day going up meant that you would wear fewer clothes, chances are one did cause the other one. But if you do an experiment, because correlation doesn't equal causation, you cannot conclude that one caused the other. Now, that's really important with correlations, that you cannot conclude that one variable had an effect on the other. So what you would do is, if you did find a strong correlation, that would be further ground for you to do research in the future. That would be a good foundation to move on. So what people do, what I'm trying to make clear here, is that if you find a strong correlation, that's good ground for you to then do a more scientific explanation, a scientific experiment to then see if an IV did affect the DV. I explain that so terribly. Now, correlations, as the screen does say, they are a method. The correlations are a method in its own right. They are. They're more of a method of analysis, but you can just do a correlation. Though some people actually use correlations as part of their experiments, if that makes sense. So we saw this with observations. We saw this with self-reports. They're often incorporated into experiments. And finally, a really crucial thing to note down is that both of your covariables must be numerical. Otherwise, it's not an experiment. So correlations only deal with numerical quantitative data. You cannot plot qualitative data on a graph. So both of your covariables needs to be numerical. Really important. Okay, so we know what a correlation is in this case. What I want to go into in a bit more detail is writing a correlational hypothesis. So if you're not particularly strong on hypotheses, you may want to go back to my video where I explained about hypotheses, or go back to the slides or my Google site, for example, or your teacher's Google site. But basically, you do need to know how to write a hypothesis. There are certain rules you have. Now, just a reminder before we go into this, for any hypothesis, or rather, I should say, for an experimental hypothesis, which we looked at in the past, for an experimental hypothesis, you need your 2 IVs and a DV, all operationalized in an experimental hypothesis. For a correlational hypothesis, you never use the word difference, right? You should always use the word correlation and relationship. So if you're going to say there will be a relationship between this covariable and that covariable, fantastic, right? But if you were to say for a correlational hypothesis, there will be a difference, boom, 0 marks. Your examiner's not going to finish reading your answer because there's no coming back from it, basically. So never use the word difference for a correlational hypothesis. You always want to use the word correlation or a relationship. Never refer to IVs or DVs because a correlation does not have IVs or DVs. It just has two covariables. And those two covariables needs to be fully operationalized. And what we mean by that is you make them as specific as possible. How exactly are you measuring them? What's it out of, for example? And you would need quantitative data for both of those. So here is a good example. Now, up the top, you've got a template for how you write correlations. There will be a significant positive or negative correlation between this covariable measured by this and this covariable measured by this. So if we've got one down the bottom, the one I used earlier, is there will be a significant negative correlation. Remember, a negative correlation is when there's an inverse relationship. So it's saying that, you know, when one variable tends to go up, the other one kind of tends to go down, although one's not causing the other. So there will be a significant negative relationship between the heat of the sun, measured in degrees Celsius, and clothing, measured by the number of clothing items worn. Both of those in green, both of those are numbers. Both of those are numbers. If you take out the green, it's not operationalized and it's not numerical. So if you were to take out the green and just say there'll be a relationship between the heat of the sun and clothing, the heat of the sun may not be actually being measured quantitatively, right? You could go to people like, you know, how hot's the sun? Oh, it's really hot. How hot is it today? Oh, it's mild. You need to make sure you're measuring both covariables quantitatively / numerically. Okay, so as you've seen from that last slide, correlational hypotheses can also be directional or non-directional. So you're either going to say there will be a relationship, don't know which way that's going to go, right? There will be a relationship, there'll be a correlation, that would be non-directional in this case, or you're going to say there will be a positive correlation, there will be a negative correlation. So directional actually states there'll be for example, there will be a positive relationship between speech mistakes measured by the number of ums, that's a number, and audience size, not operationalized, but it is now measured by the number of people in the audience. Whereas a non-directional one would be there will be a relationship. Why do you do directional or non-directional? It depends if previous research that has been consistent has been done before, right? So if you have a good idea about whether a correlation is going to come up or not. Okay, so that's relatively straightforward there, I think. You know, directional hypotheses, pretty straightforward. You've also got non-directional hypotheses just here as to why. So if you, by the way, if you still do not get directional or non-directional hypotheses, you may just want to go back 20 seconds, pause the video and have a read, because this is going through why they are directional or non-directional. But I do want to go into a bit more detail about the different types of relationships, right? Mainly positive, negative, so on and so forth. So a positive relationship, remember, is one that goes in this way. Why is it positive? Because up this end it's higher, up this end it's higher, and if you're going in that direction, generally speaking, when one variable goes up, the other one goes up, or actually kind of down as well, but I'm not going to go into... If one variable goes down, the other one goes down, it would still end up with a graph like this. Right? It would still end up with a graph like this, by the way. I don't have the time to explain to you why. Hopefully you can figure it out. But a positive relationship is where variables increase or decrease together, very importantly, though not necessarily at the same pace. It may be like, kind of one going a lot higher than another. Don't know why I did the sound effect then. Yes, we've already seen this. And then a negative correlation is when one variable goes it goes up in units, another one goes down, and you've got that one just there. So a simple explanation would be, as the sea levels go down, the number of fish that die will go up. You could phrase that multiple ways, as I phrased it earlier. Now, fine, easy. I think so far it's quite easy. This is where it starts to get a little bit harder. So, correlation coefficient is the first thing you need to know. It's a number from -1 through 0 to +1 that measures the strength of the correlation between the two covariables. It's basically the best definition I've come up with off the top of my head. It's a number from -1 through 0 to +1 that measures the extent to which you have a strong relationship between both variables. You do not have to calculate the correlation coefficient. You do not have to work it out, but you will definitely have to interpret it at some point across your 3 papers. How do you do this? So, for example, any coefficient that begins with a plus is denoting, thank you, good use of the word denoting there, Kieran, thank you, is denoting a positive correlation. Now, it doesn't mean it's a strong correlation, doesn't mean it's a weak one, it just means it's positive, right? Any correlation coefficient with a minus in front of it obviously denotes a negative correlation. Now, you have to determine the strength of the correlation. So, these are the statistics I use. Other teachers sometimes do use other ones. But any number between 0 and -0.3 or 0 and +0.3, you would consider to be a weak correlation. If I go back, excuse me, if we go all the way back to the beginning, this is what a -0.3 looks like. Like, it's kind of in the same direction. Look, there's none down here. There's not really any up here. It's kind of pointing in this direction, but it's quite weak. It's very weak. You're saying that there is a relationship between these two covariables, but it's more likely going to be chance. Do you know what I mean? Whereas this one over here is a +0.3, or in this case, I don't get maths. Maths really annoys me for many reasons. But if there's nothing before the 0, that automatically means it's a plus. You do the math. Well, don't do the math, actually, because you wouldn't be able to, because there's stupid mathematical rules. But look, generally, this one is kind of in that direction. So anything between 0 and 0.3 is a weak correlation. On the other hand, anything between 0.3 and 0.7, whether plus or minus, would be considered a moderate correlation. So anything between those. So 0.5 would be a moderate correlation. 0.6 would be a moderate correlation. 0.4.1, 0.3.7, all of these would be moderate correlations. And then between 0.7 and 1 would be a strong correlation. I should say, by the way, what does a +1 correlation mean? They're perfectly correlated. A +1, which is incredibly rare, by the way, a +1 correlation is essentially when one variable goes up, the other variable goes up by exactly the same amount. Right? Exactly the same amount. Now, I've got to be honest, chances are, if you've got a +1, chances are that you have sorry, I forgot I was doing that. You have found a causational relationship. You know, clearly one is affecting the other here. But again, because it's a correlation, you can't actually say that. So what a +1 actually looks like is essentially this here. Right? Perfect. Right. What we're looking for is probably more like this. If you find this or this, for example, chances are you have actually found a pretty strong correlation, and that would be grounds for you to go off and do more as scientific research, such as a correlation. Now, there's some examples there. I would like you, please, to look through those and just make sure you understand them. Right? Do you get that 0.981 would be a strong negative correlation? Do you understand that plus 3.56 would be a moderate positive correlation? So a piece of advice, by the way, and again, something to note down, is that if you are trying to write a correlation coefficient, you kind of need two descriptive words or adjectives or adverbs or nouns, whatever they are. I think I missed that day in school, to be honest. But moderate positive, moderate negative, weak positive, strong negative. So you need those two adverbs, adjectives. I don't know. So quite an important point there, I think. Quite an important point as a reminder. If you need a correlation, then yeah. One thing I don't have in this slide, actually, which I do need to change, and I will change after this video, is evaluations. What evaluations are there for a correlation? So you don't need massive amounts, but one that I would go for is that it's a weakness that you cannot. It's a weakness that you cannot infer cause and effect relationship. Cause and effect, kind of. I guess they are relationships, but you can't say one affects the other. So that the fact you can't do that reduces how scientific correlations are. A positive correlations is that they actually act as a good foundation for further research. If you find a strong correlation, that is actually a good reason for you to then go away and do more scientific experiments to see if you can see the IV affect the DV. Correlations also, finally, work quite well with other research methods, so they can be used with experiments quite well. They can be used with observations quite well, and self-reports quite well as well, because don't forget, self-report often collects quantitative data. So actually, well, I don't want to get too over the top here, but correlations and self-report are often used together because correlations are quantitative data, right? How do you think you're getting that data? Right, through self-reports most of the time. So that is pretty much it, to be honest, with correlations. The only other thing I probably might want to add is you need to be careful for the 12 markers at the end of paper 2, where you were asked to design a whole study or most of a study. One of those could be a correlation. So you need to really know and wrap your head and understand correlations, because you may be asked to actually design a correlation at the end of your paper 2. Peace out.